not recording over there. You need audio over there on the recording too. That'll help a lot. Last week we started talking about JSON as a data structure and how we can use JSON to share data between applications or between a web server and a web client, all that kind of stuff. We started looking at how to get data out of our Postgres database in a JSON format to enable easier integration and development. Today we're going to actually store data or store JSON data in our database. So there is a JSON data type. In fact, there are two JSON data types, which we'll talk about in a second. So if we look at those, we're going to go through 2 slides of stuff copied from the Postgres website with my commentary as added in. So the JSON data types are used for storing JSON, JavaScript object notation. If you feel like reading the RFC that specifies what JSON looks like, you are welcome to, but we are not going to do that now. We did a quick rundown of that, how it's got string data types and integer data types or numeric data types and nulls, arrays, and objects. That's pretty much the RFC. We could use a text field, a text data type to store our JSON structures, but you don't get any advantages of a specific data field built for JSON. JSON is a structured data set, so it's not like the text of a book, which you would typically store in a text field, but instead it is a structured data type. So there are 2 JSON data types. There's one called JSON and one called JSON-B. B is for binary. To implement efficient query mechanisms for these data types, Postgres also provides the JSON path data type. We won't talk about that. So JSON and JSON-B, what is the difference? JSON stores the raw JSON you put into it. So JSON is a text format. It stores the raw text. It does this so if the order of your keys, if the format of the string itself is important to you, you can store the raw JSON that you have to begin with. Usually we don't do that. Because there's a JSON-B, the JSON binary data type, which actually parses the JSON itself into a structure of some sort, which will then allow us to access the fields in the JSON much more efficiently. You can do that on a JSON data type as well, but from a JSON, the plain JSON data type, all of that processing of the keys and their values happens at query time. So you can imagine at query time, it will be significantly slower to parse the JSON, find the fields you're looking for, and extract the data, as opposed to a JSON-B, which it's parsed and processed on input. So when you put the data into the JSON data type, it's parsed and stored in a magical data structure, which makes getting the data later much more efficient. And I'll show examples of how we can get that data. But if you actually read through this text, that's pretty much what it says. The JSON data type stores an exact copy of the input text. Processing functions, so querying, updating, etc., using something in a where clause, must reparse on each execution. While JSON-B is stored in a decomposed binary format that makes it slower on input, but much, much faster on querying and updating, since you don't have to reparse every time you access that data. And the big winner here, which we haven't really talked about at all, and so we're going to talk about this tonight too, is you can build an index around a field on a JSON-B structure. And I'll show you what that looks like. Again, we haven't talked about indexes, but I'll introduce that tonight. So I covered most of this already. JSON is raw. JSON-B is binary already. The only reason you would really, from their documentation, and I tried to think of other examples, but if you care about like that order of keys, so JSON is a key value pair in an object kind of structure. If the order of those keys matters for some reason, then maybe you would store the raw data. But that is very, very rarely a case. Like, I don't know why you would care if first name came before last name, or last name came before first name in the actual structure, because you can do things like sorting and reordering those keys when you query or when you present that data to someone else. JSON structures have a native mapping into a Postgres data type. So a JSON string natively gets stored as a text object or a text data type in Postgres. The numbers in JSON become a numeric type. Booleans are Boolean types, and a null JSON type doesn't get stored as a value. So this one I'm not totally clear on. I would have to play around and see what happens. But I have a feeling it gets stored as a null, but that line of description kind of indicates otherwise. But we can figure that out when we play around with our JSON later. Any questions about the difference between JSON and JSONB, or is the concept still too abstract?
Do you define parsed for me?
Yeah. Trying to think of a good way to do that. I know how we'll do that. You don't need to see my brother's text messages to me. So JSON structures. So if I have an object with a key first name and a value Chris, another key last name value Fauerbach. This is a valid JSON structure, right? I can prettify it to make it look better. When I store this in a JSON data type, all it does is it makes sure it is valid JSON. If this were not valid JSON, I couldn't store it. I would get some sort of an error. So I'm using a different tool here to show the same concept. JSON Lint is a website that just helps you helps you look at JSON structures to make sure it's valid. But a JSON data type, when you're putting it in, the only thing that happens is it makes sure it's a valid JSON structure. So if you have a valid JSON structure, it will get stored. Then when I query it, I can query a JSON data type and pull out the first name attribute. So on a JSON data structure, when I query, this gets processed or parsed, and then it can pull out this first name attribute. So that's the processing. As opposed to the JSONB structure, when I insert it, it's made sure it's valid, and then it's processed into its component parts. First name, last name, any other attributes associated with it. So when I query, all that parsing is already done. So the big advantage is it only has to parse and process it once as you're putting it in, as opposed to a JSON data structure, which parses it every time I query it to find what attributes it has, as an example.
Got it. Thank you.
Yeah, and we'll show as we go through more. I'll show what other parts are in there. So here's a little bit more on parsing strings to JSON. Like before, we were bringing our rows from our query back as a JSON structure. But let's close all these. Come on now. Always forget the password. There it is. Is this connected? All right, so let's look at this simple query, if you will. Was that me echoing, or did somebody have a question? Cool. Something you can do with most SQL or most relational database engines is execute a select statement, but without like a from clause, without a table. Because in this case, I'm giving it all the information it needs. So normally, I can select a string, and I get back a string. I can also explicitly cast that to JSON on my way out. I didn't like that for some reason. It's using Postgres. Well, whatever. I'll ignore that for now. You can execute these statements to get a JSON structure. What it does is it takes that string and parses it into a JSON structure. So it's an explicit cast. So here I have a string that looks like a JSON array, and when I cast it with this JSON : JSON structure, it becomes a JSON array. Do I have my PG admin open? I think it's running, but when I do that, it doesn't give it to me. 50-50, maybe? Yeah. I'll try that again later. Let's keep going. So here's an example. No, I really need this to work. Of a quick table with some JSON in it. So I'm creating a table called users, and I have a typical ID, first name, last name, phone number as all as varchars, and I'm adding a metadata field for JSON B. The reason I'm using JSON here is that this metadata, I don't want it to be a standard structure like everyone has a first name and everyone has a last name. I want it to be a little flexible. So I'm putting things like favorite color into that field, or interests, or dislikes. But not every row in that table has to have the same structure in their metadata. So let me see if this works. Okay, good. That worked. So I can insert that data into my table. So just showing you what that now looks like in the table. I have 3 rows, 1, 2, and 3, and my metadata looks like JSON. Right, I have a JSON object. I don't know if you can see that very well, but at the beginning it's the curly bracket, open curly bracket to show that it is a JSON object. Double quotes around a key value. The key is interests, and the value is an array of strings: gardening, beekeeping, teaching, etc. Another one of favorite color, with a purple as my favorite color. The second one has a different attribute, dislikes, but it also has interests and favorite color. The third one has interests and favorite color as well. So you can see that it's not a defined structure, meaning it's not like a column in a table that has to exist on every row. Whether it has a value or not, it has to exist. Like it can be, rows can be, or columns can be nullable. But here I can put in whatever I want. There's no rule yet for what that structure has to look like. And the way I insert the JSON is the database engine knows it's a JSON B field, and the value I insert is just a string. So it's a string surrounded by single ticks to indicate it's a string, and inside of it is a string that is valid JSON. So it's super easy to put that data into the database table.
Can I ask you a question?
Absolutely.
So, if you were strictly using a database, would it be pertinent to have the metadata, or would you just, would you only incorporate the JSON metadata if you were, I guess, parsing it for some other application or use?
No. So if I'm only thinking about my database structure, and there are, depending on the data I was modeling, I could use a JSON structure because it's kind of a generic structured data type, but that doesn't have a predefined set of columns or anything like that. So you'll see this primarily used for things like, as an example, I used to work for an insurance company, and our insurance policies had a very well-defined structure, right? It had the name, it had the thing insured, it had the value, it had the deductible information. Like, it had 10 fields that were common across every single insurance policy in the universe. Since it was a specialty insurance company, though, there had to be flexibility in the data model. Otherwise, you would get into a database that had 7 million different fields, but 90% of the time, they wouldn't be used. And so you could use a JSON type structure to say, I need to keep track of this data in an organized way, but I don't want to prescribe my database to restrict that to something that we may not think of. Tomorrow we may need to add some new concept, and using a generic field like this makes it easy.
Yeah,
So
I was thinking about if something had a varying quantity of attributes and you didn't want to have a separate table for a million different things, or
exactly. Yeah, you certainly could use something, a structure like this. And I'm going to kind of contradict 3 slides from now, but you would use this really for data that it wouldn't be your like primary lookup fields, right? Everything has like an ID, so you'd usually look for something by ID. If I'm doing a yellow pages, right, everything's going to have a name, so I'm always going to have a name field. That's super important. But if you want to have stuff, extra data associated with it that you would probably not really use to find an individual record, that would be a decent candidate for your JSON structure. So it's the flexibility is really the key around it. Great question, though. So there's a lot of ways we can interact with our JSON structures. This is where it starts to get fun, in my opinion. So let's start with a query. Here's a normal query that we would build. I'm getting first name, last name from users, but you'll see this third column or third thing I want to pull out of my data. It's an attribute on that metadata, on that JSONB field. So I want to pull the value of the interests field. And so the structure to do that is give the name of the column, hyphen, arrow, then the name of the column. So when I run that, I get first name, last name, and then the value that was in the name of that column. That column was interests, and so I got the values from interests. Cool?
And what are we gonna get when the name of the column is not there? I mean, for example, for the first one.
Awesome. Awesome question. So let's change that. Let's change it to dislikes. Is that what it was? Here, I'll just make up crap. I don't have an AFSD. I don't have that field anywhere. So let's see what happens when I run this query. I get null returns.
Okay, thank
We can use it in a where clause as well. Select first name, last name from users where metadata favorite color equals gray. So this is where I'm kind of contradicting what I was saying earlier about searching by these fields. You totally can do that. And I'll tell you how to make it better in a little bit. But you can. You can execute this, and I will return the person whose favorite color is gray. Debbie Downer obviously likes gray. But the syntax is the same. The column name hyphen greater than name of the field or the attribute, and then like any other comparison equals gray. This one is another new character for us. So we've looked at equals, greater than, less than, not null, all those kind of comparators. But this is a new one. It's a question mark where I want to find the record. I know interests is an array, right? Interests was an array wherever it was. I want to find every interests list that contains the string beer. So I want to find all what? Oh God! So this is a SQL developer problem because it's trying to parse this as Oracle, but it's not Oracle. So stop doing that. All right, I really need my PG admin to work. Please work this time. Come on, buddy. Hallelujah. Where was I? There's my beer. Okay, so let me try that again. There we go. All right, just as a quick reminder, this is what my data looks like. So my interests field on all those records is they're all arrays, right? This one has 4 values in the array, this one has 3, this one has 2. The next query is going to say, give me the results where interests contains the string beer. So this is not a string contains, like looking for beer inside of a string or a varchar. It's looking for the string beer in the array. So what should get returned? Whose interests contain beer?
Second.
Yes, Chris's do, but not in the database. So Joe Schmo's interests contain beer. And so we get Joe Schmo as a result.
Excuse me, why did we write JSON B?
Great question. Because it requires us to. If we don't, let me show you what happens. And I don't know why this is the case. Oh yes, I know why this is the case, I think. If I don't, then the database engine on parsing of this query does not know what that field is. Since it's not a predefined field with a data type, it doesn't know what it is, So I try to execute this, and it says, no operator matches the given name and argument types. You may need to add an explicit typecast. Because the database cannot figure out what question I'm asking, really. So I have to tell it metadata interests is JSONB.
But we already wrote the type when we created the table, right?
Yes, the column type is JSONB. But for whatever reason, it can't then infer that the attribute within the JSON structure we're looking for is still JSON. And I don't know why. But that's the limitation.
Okay.
So when I do tell it, when I cast it to JSONB, it works. Now that my PG admin is working, I want to go back to this casting concept here that I super skipped because JSON or SQL developer didn't like it. So this is what casting is. So I can take this string 5 and cast it to a JSON data type. So it knows it's JSON now. Same thing with this string. If I don't cast this string, then I get a text column as my result, right? It's the string that is in that list. If I do cast it, now it knows it's a JSON structure. Same thing with all these. I am selecting, when I highlight part of it, it just executes that part of the SQL. So I highlighted just the text and it returned a text type. But when I explicitly cast that text, then I get a JSON type as my return value. All right, where was I? So that was the whole point of this, was casting. Oh, I had more. I got beer already. So I can also query to find users. I'm counting in this case. Let me just have that thing up again. Select. So here's on my users table again. This query says count star from users where metadata. Notice I am not performing this cast here, but I'm looking at the metadata field itself, not metadata interests. Just metadata itself contains dislikes. So when it's this, when you're querying the column itself, you're querying the fields, the attributes of that JSON structure. So I'm saying which users have a field dislikes in their metadata. And again, it's going to be, it should just be one for Joe Schmo. Just to show the data. So Joe Schmo was the only one that had a dislikes attribute. Off the top of your head, can anyone think of a use case where that would be helpful?
Using JSON?
No, specifically a query like this, where I'm looking for rows that contain a certain key and excluding rows that don't have that key. Like, when would that be helpful?
Querying a large database.
A large database, but for what purpose?
Maybe if there's some type of person database, you could have a field that has, array of the person's kids' names. If they don't have kids, then they get excluded.
Mm-hmm. Yeah, so I'm only querying folks that have kids. Or if think about like a shopping website like Amazon, I'm only going to look at things that have, Prime. That's Amazon Prime, and there are different types of Amazon Prime. So maybe it doesn't matter what's in it, like if it's Prime 1 day or Prime 2 day, but the fact that it has the Prime attribute, could be a filter on the website. A lot of these things.
Dating apps, I feel like.
A dating app? Yeah, right?
You have certain criteria to.
Yep, exactly. And that goes with this one kind of too, right? Is I'm only going to date the folks that like beer, because if they don't like beer, they're no fun. So I don't want to date them, right?
Can't trust them.
Exactly. And so those are kind of the use cases you can have here. Otherwise, you're going to be building a database structure that has a one-to-many relationship to a person and their likes, then another one-to-many relationship between a person and their dislikes. But that dislikes table doesn't really give you any value other than creating an array of dislikes that you can query. And you can do it in one structure without having to predefine all those other things. The problem could come, though, is when we do data modeling, we could get lazy and just make everything a JSON-B structure because we don't want to predefine our database. And there are actually database engines that's basically what you do. They're called document stores or columnar databases. But in a relational database, like 95% of your columns will not be a JSON structure, because we use relational databases to have all those rules on data integrity, on relationships, and constraints on our fields and all that kind of stuff, where I think you lose a lot of that when you move to a JSON type structure. But you always use the right tool for the job, and sometimes that generic data structure is a good attribute of a well-defined structure. In this case, our users, our first and last name, that's a really well-defined data structure. We could expand that to phone number and address and all those stuff that needs to be of a certain format with relationship rules and all that. But sometimes that extra data is needed without a full database structure behind it. Okay, and then another one that is kind of neat. Whoops, where did I go? So, was that a question?
Yeah, just real quick. So, for instance, like if we had a field named interest, and Joe Schmo has 3 interests, and like there would be 3 rows for Joe Schmo, and whereas with JSON-B, like it could just be one like free text.
Yeah.
Is that a good analogy? Okay.
Yeah, exactly right. Because like for the dating app, maybe that's not a great example. I like it though, because like tags. Ooh, tags is a good one. I think in today's like world, everyone is familiar with the concept of like hashtags on Twitter, where it's just random crap, right? Or if you're doing a blog post, you can put a bunch of tags. It helps searching and all that kind of stuff. You can use those to find the information you're looking for, but more often than not, you're going to be finding the actual article by a direct URL, right? You're going to click on a link with the ID in the URL, and that'll get the important things like the author's name, the content of the article, and whatnot. But the tags is kind of like an optional, helpful thing that is stored in the database, but not really required. And it's kind of optional stuff. I like the word optional for that. It works out well in my head. So I think the last example of querying this data I have is this. So if I want to pull the interests for user ID 1, I can do that. And I get back a JSON structure, which could be what you need. Sometimes if you are building that API or you're building, a spreadsheet, let's go with spreadsheet. That's a better example. This format isn't really helpful. So there's a function called JSON B array elements text, which can take that JSON array and kind of turn it into a result set of its own. So now instead of one record being returned with 4 values in it, I get 4 records being returned, each with 1 value in it. So if you were making a unique list of interests, you would need to have it in more of this result set format as opposed to one array, specifically unique across multiple rows. And that was the example in my head I came up with, and I'm kind of curious if I can do a distinct in front of that to see if that actually works. I can. So now I can take away my where clause to get really all of the interests for all of my users. So it kind of turns this, it takes that array and breaks it up into multiple rows. Now how that works with other fields, I'm kind of curious about. So if I wanted a first name list, I am going to get those relationships. So I'm not doing some weird Cartesian join, but this is turning it into a one-to-many model. Cool. All right. Any questions on that?
Chris, can we convert the rows to columns? I mean, we have multiple addresses. So I want to insert each address in one column beside the name itself. Is it possible?
That's a great question. So let's see. This is JSON-B array elements text. Postgres SQL JSON functions. Let's find that function. Let's see if there is a kind of the array element text type of to record. Builds an arbitrary record from a JSON object. Select star from, oh, that's kind of neat. JSON to record set. A1, A, B. Oh, so that's kind of cool. We could do that. So let's do that in a second. So I don't know what this will do for the interests itself. It might not work. Okay, it didn't work. But if I do this, no, JSON-B record set, the function returning record called in context that cannot accept a record. Hint: try calling the function in the from clause using a column definition list. That's weird. Select star. Oh. Select star. Select star from. Users metadata? I'm totally guessing here. I'm trying to figure this one out. Missing from clause. Okay, JSON the record set. This is the JSON itself. Oh, it needs an as clause. Okay, that's not what I wanted to do at all. Array elements, object keys. Each expands the outermost JSON into a set of key value pairs. Key value AB now. JSON each expands the outermost. So no, I don't think it can take those array elements and turn it into columns. But I'm going to research that one more because that sounds like a good thing to do. No, it doesn't. No, it doesn't.
Research it later.
No, yeah, no. The reason I just came to like it doesn't make sense to me in this case. Let me get this written out. The values in this array are strings. For that string to become a column, what would there would be no value for that field. Yeah.
So maybe we have to name the field and assign a type for it before.
Well, yeah, but like if gardening, as an example, were a column, right? If I went back to just where user ID equals 1, just to keep it a smaller data set. If gardening were a column, what would the value be in that column field?
I guess you didn't get my question. I mean, for example, if the first person had like 4 interests, okay? I want to assign each interest under one column. For example, interest 1 equal to gardening, interest 2 equal to whatever.
Okay.
Yeah. But it's okay, never mind.
No, I see what you're saying and how that is a little different than what I was saying. That would be more like the other query where I was just pulling the interests. And enumerating each of those as a column. But the column name could be interest 0, interest 1, 2, and 3. And for here, interest 3 would be null, interest 2 and 3 would be null on the last one. That makes sense. That I'm going to figure out. After class. JSON.
Thank you.
Yep. All right.
Professor Kuros,
Yes, sir.
I was gonna ask so can you make that column foreign key, and if so, distribute that? No. Because that would kill the need for many-to-many join tables.
It could, yeah. No, you can't do a key. I don't even think you could do a primary key as a JSON field, but let's find out. Data JSON B primary key. Guarantee.
Right?
Well, no, not necessarily, but okay. Data reference data JSON B references test data, right? Really?
Oh man, did I just break info 610?
No, you just broke my brain. Why? I don't know why the hell you'd ever do this. Like, but the fact that you can is interesting.
Well, I was just thinking, so for instance, for my project where I'm going to be doing sort of like a property management database.
Yeah.
I have one house that has several associated contractors and another house that has several associated contractors. Well, at that point, instead of needing to create a many-to-many table with house contractor, house contractor, house contractor,
Yeah.
line,
Okay. So there you don't want the column as the
no, I don't want the column as the primary key. I want
Right.
the column to contain a list of foreign keys.
yeah, you want the
Right.
values in the JSON array to be the foreign key for the other table.
Exactly. And at that point, then you wouldn't need that, join table to satisfy that many-to-many relationship.
Yeah, now I'm curious if we could come up with a way using our own constraints to do that. Interesting. I like the idea. If you could, you save a table, but I don't know if you can. But I also didn't know you could do that. So maybe. All right.
Does that mean I only need 9 tables? Because of
No, you still need 12. 10 is the number, right? But I want to make him have more work. All right, so the biggest advantage that the Postgres website talked about for using a JSON-B, or one of the biggest advantages, and this goes to completely counteract or contradict what I said earlier about using these fields to search. We can use these fields for search, but to do it, we have to create an index. So imagine a world where we have a test1 table. In that test1 table, this is not JSON specific. So kind of put JSON on hold for now. We have a table called test1, ID and a varchar content, right? The content is a string. Now that table has 3 million records in it, where the ID, in this I should have written out serial primary key, but the content would be a word or any string, it didn't matter. But there are 3 million of them. If you execute a query like this, select star from test1 where content equals name. Anybody know how the database engine would find rows whose content equaled name?
I guess sequentially, one by one.
One by one. That's exactly right. So it has to search through every single field in a row completely, start to finish, to find every row whose name was content, or whose content value was name. The best way I could think of really nailing that idea was if you took your favorite book and had to find every instance of the word the in your favorite book in the English language. How long would that take?
however long it takes you to read the book, plus how long it takes you to log every instance of the word the.
So let's say given a 400-page book, no, I read a lot of Stephen King and Brandon Sanderson. Brandon Sanderson books are 800 pages long. How long would that take me? That would take forever. An eternity. A computer could do it a lot faster, that's for absolutely sure. But still, it has to go record by record to find every word, every content whose value was name. Has anyone taken any programming classes and know what big O notation is?
Yeah, but I can't really explain it very well.
Well, that's why I'm here. So the concept of big O, it's a way of measuring the amount of time or the amount of cycles or the amount of processing that it takes to perform an operation on a set of data. So big O-N in this format, really it's this format, means the amount of time time is an oversimplification, but the amount of time it takes to perform this operation on a collection is directly related to the number of elements in the collection, n. So if there were 10 items in our table, it would take 10, however long it takes to analyze one record, right? It takes 10 times that. If I have 100 records, it takes 100 times whatever time it takes. Let's say 1 unit of time. It takes 100 unit of time. If I had 3 million records, it takes 3 million units of time to scan.
So n is the number of rows.
It's n is the
number. It's not like the matrix. It's not like column time row.
Correct. Yeah, but it's a linear relationship, right? That's the important part. It is a linear relationship to the number of elements in the table, in the collection, because it's a generic concept, not just a database concept. So if there are 3 million records in this table, it takes 3 million units of time to search it. That can be super slow. The bigger your database is, the slower it is to search your database. And indexes in our database are how we fix this. So from Wikipedia, therefore theoretical, like super smart stuff that would probably take me a while to get through, I'll read the first couple sentences. A database index is a data structure that improves the speed of data retrieval operations on a database table at the cost of additional writes and storage space to maintain this index structure. So if you think about the back of your book, like a textbook, if you want to find every mention of a keyword like table in our database book or stored procedure, whatever, in our database book, we'd flip to the index at the back. We'd say, okay, cool. Stored procedures are talked on page 17, 103 through 108. Like that index allows you to go straight to where the concept is that you're looking for. Now, it took someone time to update that index, so you can look at it faster later. You can find the data faster later. Is everybody tracking with that? The time spent up front, like the two concepts in here that I'm hitting on. The additional cost, right? Writes, meaning someone had to make this index. Someone had to say, okay, stored procedures are on page 17. That's someone's time. Then they had to put it on paper. If you didn't have an index, you wouldn't have those 4 pages of paper in the back of your book. It's the exact same thing in a database. When you're inserting data into your database and you have an index on a field, it takes a little bit more work to add the new value that you're inserting to your index and a little more disk storage to keep track of that index. So, if we went back to that table, our test 1 table with our ID and content, I can create an index. I can give it a name, test 1 ID index, on the table name and the column. Indexes are for a column or set of columns. I can create 2 indexes, multiple indexes on the same table. Here I'll create another index on test 1 content. So in this example, if every row in my table is a word in my book, then I've just created a lookup field or an index to help me find specific words. You with me?
So like this table would have like all the, like a column that says words, and so like it would say the, and, but, or, and then it would have like a column that counts it or that gives like a location.
It's not on the table itself, it's somewhere else in the database. So one thing I love about browsers like pgadmin or SQL Developer is I can look at my database structure, not just my tables, but the other things in there. And indexes are an attribute of the table. So if I look at here we go. I'm looking at my tables. On my test table, I can look at my indexes. In this case, I have no indexes. But it's an attribute of the table, but it's not a column in the table. The reason I do that is now I can look up content in there very, very quickly. So yeah, so that's the index in the back of our book. So if you can imagine, we have a book written out like my 800-page Brandon Sanderson book. If I had an index at the back of the book that listed every unique word and what pages it was on, it'd be a really, really big index on paper. But on a computer, it's not very big. The computer can look at that index really, really quickly to find what you're looking for. And so going just quickly on that O notation, now instead of an N where the time to find that data is a linear relationship to the number of records in that table, now I just have to hit my index. And the database engine knows I'm querying the content column, and there's an index on the content column, so I'm going to look in the index first, and that index then will tell me exactly where in the table those records are. So that is a fixed size, a fixed unit of time, regardless of how big my table gets. That's an oversimplification, but that's pretty much accurate.
Is there, oh, excuse me, Mr. Chris?
Yeah.
Is there any, I guess, sort of formula or anything behind how to decipher how much extra storage that you'll need for an index on a certain number of columns?
Yeah, and Postgres gives you stuff like that, calculating index sizes. Because if you were a database administrator, that is very, very important to know. Tables I work on that keeps our messaging history. I have billions of records in that table. So the size of the index is important. And looking here, some weird DBA kind of things, you can find the size of your index with this type of query.
Awesome. Thank you.
Yep. And if this were a DBA class, we could go into this level of detail as like standard part of the class. But in my theory, it's more important for y'all to know how to use the user end of the database, not the administrative end of the database. But if y'all feel otherwise, I'm certainly open to exploring whatever y'all want to talk about. But I think that the intent of the question was right on. That got to it can be important to know how large your index is based on how large your table is.
Thank you.
Yep. And then DBAs can do cool things like they can put an index on a really fast type of hard drive, like on an SSD or a high spinning RPM drive, and then the database data itself can be on a slower drive or a network drive or something like that. Like you can get into some pretty cool ways of partitioning this data and getting fast access to it. And so the reason I wanted to talk about that, well, let me make that as an example. Let me go through this. If I have a table like this, my test one table, I can then create an index on the content field. As a note, there is no data in this table, so creating an index is a super fast thing. If this table had 3 million rows already, and then I created the index, it would take a long time for the database to properly index all the data that's in the table. But now, since I've done it before I put data into it, the inserts, the creation of the indexes is near instantaneous. There's just almost an immeasurable amount of time added to the insert of my record. One thing I wanted to show, if I select all my data from test 1, it gets me all the data. Let me see if this is the right format. Okay, so we haven't talked about what explain means, but this is how you figure out when you need indexes. Explain is a command to the database engine to say, what happens when I run this query? So it's multiple steps typically, but in this case, it's telling me I'm doing a sequential scan on test 1. Sequential is bad because it's step by step through all the tables. And so that was just a select star from test. If I throw in where content equals my explain, it's an explain plan, my query plan should change. Now you can see it changed. I don't have a sequential scan anymore because sequential scans are really bad. Step 1, a bitmap heat scan on test 1. That's the index. Then I'm checking that index for the word the. Then a bitmap index scan on the index and the table. Maybe I'm going backwards. It's a bitmap scan on the index and then a scan on the test based on the index. So it's a much faster way of querying your table. And if I had 3 million records and we actually ran some queries, it would be very, very evident how much faster that kind of query would go. So we can work on explain plans later more. This gets super critical when you're, first to find those sequential scans because they're never a good thing. Unless you have like a really, really tiny lookup kind of table, then it's acceptable sometimes. But really you want to index everything at the expense of disk and memory and all that stuff. But indexing things you're going to query is really critical. Primary keys themselves don't naturally get an index, which is interesting. So if I create, how's our time? We got a couple minutes. So if I create this table test 1, and I come over here and I look at, let me refresh this, I think. And if I look at test 1, I have my primary key constraint, but I don't have any indexes. When I add my content index, then I now have an index, or I should have an index. Oh, that's test, that's not test 1. Where's my test 1? There's my test 1. Now I have this content index. But still, if I were going to search by ID, I still have to do oh, maybe there is an index. I didn't think primary keys got natural indexes. Index scanned using primary key. Okay, forget I said that. But it's not listing the index, so I guess the primary key constraint did give it a index. Well, that's good. Foreign keys. Is it foreign keys aren't indexed? Maybe they are. Whatever. I can be wrong sometimes. But test things out and you'll figure it out. So the reason I wanted to throw in that index conversation was you can create an index on a JSONB field. So with a statement like this, I can create an index on a JSONB field, which in this case would be data, unlike metadata earlier, but specifically the index or the interests field. So now if I'm searching a user table with 3 million users in it, and I want to find people who have an interest in beer, it becomes an index search and not a full table scan. See why I had to do that whole index thing just to have that one line. So that's a way of speeding up those searches on a JSON field. And you would do that on exactly the use cases we talked about earlier. Searching by someone's interests, searching by tags, searching by likes and dislikes, etc. And that is it. And so no explicit homework. I'm going to stop my recording real quick.